The third question on the quiz, number 3, is a review question, and the other one relates to what we've been doing lately as well. So, obviously, what we're about to do today is important. Yes?
Did you say at the beginning of that sentence, I couldn't hear you?
Basically, the quiz is going to have 3 questions, one of which is going to be like exercise 2 on today's Do It.
Okay.
One of which will be a review question, and from some time during, you'll have to do with equations, not quadratic. And then one will have to do with linear, exponential, quadratic, and being able to identify each.
And when did you make this quiz?
I made it while Melissa was in the bathroom. All I do is, listen,
Not in
You
the
just
potty?
wanted that on recording,
No.
didn't you?
all I do is take old Regents exam questions and put them on, and I tweak them a little bit, change them to go from A to B to C. Okay. Guys, listen, I appreciate the fact that everybody seems to be in a chuckling good mood, but we need to get this stuff down pat. Now, it went really well with the last class, so I suspect it'll go really well with you. And they were able to have some time near the end of the class to get started on their homework. So, early in the year, we did a ton of what I would call skill building. And now what we're trying to do is we are trying to learn to take those skills and apply them to new problems. And I don't think these are going to be particularly difficult questions based on what we know. Now, the first do it question is exactly the same question we had yesterday. But I wanted to emphasize the whole 2/3, 1/3 thing for a second time because I feared that maybe we wouldn't understand that, okay? Radioactive substance decreases in the amount of grams by 1/3 each year. If the starting amount is 1,452 grams, write a recursive formula for a sequence that models the amount left at any point in time, blah, 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 blah. Okay, so, what's the significance of the 1452?
This is first term.
First term, and how do we represent the first term?
A1.
A sub 1 is 1,452. Good. Now, when I write a recursive formula, I say the new term is, and then something with the previous or old term. Now, what's going on in this problem?
It's decreasing by 1/3.
Which means what part remains?
2/3.
2/3. So there is your recursive formula.
Yay.
Remember, you could have also written for the last part of this. Okay, that's perfectly acceptable as well. Okay. Any questions?
No,
Okay. So now let's get to exercise 2. And as I mentioned just a moment ago, there will be one question on the quiz that is similar to this. Oh, come on. A rare coin appreciates at a rate of 5.2% a year. Now let's just pause at this moment and ask ourselves, do you think appreciate means increase or decrease? Increase, good. If the initial value is $500, after how many years will it reach its value across the $3,000 mark, or will it hit 3,000? Show the formula. That's what they want you to do. You know, I'll give you a funny, just a cute story about rare coins. My grandfather, when he died, or before he died, he said to me that he had money hidden under his stove. He said they were all coins. And he said, you need to make me a promise. He said, I want you to promise that the day I die, the minute I die, you will go under that stove, you will get those coins, you will take them home, and any of the grandchildren, that he has like a quarter for every state, he said, I want you to finish their states for me. And then he said, then you just do the right thing by these coins. No problem, no big deal. I go in there, I grab all the coins, I bring them home, I look at them, silver dollars from 1840, 1830, buffalo nickels. They used to have buffaloes on them. They're just wild coins from way, way, way back when. So I don't know how much they're worth, but I have them in a safe, all locked up.
Why don't you put them in the museum?
I have to ask myself what my grandfather would want. That's really the whole key to it all. He also put me in charge of $15,000, or actually $20,000 for the grandchildren in the family, and my job is to disperse it as needed. But I have, like, he would never give you money to go to Disney. He just wouldn't do it. He would never give you money. I'm going to Yellowstone, I'm hoping, this summer. If I run out of money and I can't do it, he would never say, here, take $2,000 and go to Yellowstone. He would never give money for that. But if, for argument's sake, you spilled ink on your carpet and now your carpet was completely ruined, he'd buy you a new carpet. So it was just strange that way. And I wouldn't even call it strange. It was very practical. It was very practical. And so now I'm in charge of giving this money to the grandchildren in the family based on need and what they need. Like my sister at one point, oil tank broke. So I went down and bought her a new oil tank with the money, that kind of thing. Okay. So anyway, we want to come up with a formula that models this. Now, my first question for you is, do you think this is going to be quadratic, linear, exponential? What do you think? What do you think?
Linear.
Why linear?
Oh wait. Yeah, linear. Because it's not like. Oh wait, no. No, it's exponential.
It is exponential. It's not linear. Even though you say it's a constant rate of 5.2%, you're not taking 5.2% of the same number every year. Like if on year one there's $500, on year two there's about $526. On year three maybe there's $560. On year four maybe there's $610. So each year you're taking a percent of a bigger number. That's why it's not linear. Okay, you're not going to come up with the same number every year. So since it's exponential, we know the general exponential form is y equals a times b to the x, where x is the amount of time and b is going to be, let's do y equals, a is always the principal, so it's the amount we start with. What is the amount we start with? 500. And this is always going to be 1 plus or minus the percent as a decimal, and then t is the number of years. Now, I asked you what you thought appreciates means, and you told me increases. So do you think I'm going to use the plus or the minus? The plus, obviously. That's the one that increases. Minus would not increase. Now, this says 5.2% per year, but I have to express that percent as a decimal. So what is 5.2% as a decimal? Ashley, head in the game here. Come on. 5.2% is decimal. Go ahead.
0.52.
No.
Or 0.052.
0.052. So now I get 500 times 1.052 to the t, and I can't forget my y equals. So there is my equation or my function. Y equals 500 times 1.052 to the t power. All right?
Where'd you get the one?
It's always,
It's
the
always up.
one is the initial, it takes into account the starting value, and then you're gonna go up or down from there. All right, anything else? All right, so again, on your quiz coming up, you're going to have a question like that, where you're going to need to put it into exponential form and put each part where it belongs, whether it's time, whether it's initial starting amount, or whether it's 1 plus or minus, depending, like if I said depreciates, what do you think you would do?
Decrease.
Decrease, minus. What if I said it's increasing, then what would you do? Plus, and decreasing you would do minus, okay? All right, so now what we're going to do, again, we're not teaching you anything new today. What we're going to do is take what we already know and apply it to situations. So I'd like you to take just a minute to read over the first page, and then we'll talk about it. But I don't want to forge your head until you have read what it's about, so go ahead and do that.
Aren't there like billions of people in the world?
Yeah, but if you look at thousands of millions, that's called billions.
Oh, that makes sense. That's a weird way of wording it though.
Yes, it most definitely is, but there's a reason for it, and I think you'll discover that as we go through the problem. It's trying to teach you something. All right, so Callie and Joe are examining the population data in the graphs below for a history report. Their comments are as follows. Callie, it looks like the U.S. population grew the same amount as the world population. But that can't be right, can it? Now, first off, if you look at the two graphs, do they look like they grew pretty much the same? Just superficially looking, yes, superficially they look more or less the same. Joe says, well, I don't think they grew by the same amount, but they sure grew at the same rate. I mean, Joe's saying, just look at the slopes of the graphs. It's got to be the same amount. Is Callie right?
No.
No, why not?
Because that's millions.
That's thousands and this is hundreds.
Right, they're both millions overall, but that's thousands of millions and this is hundreds of millions. So that's why
they didn't grow by the same amount. And the next question says something like, is Joe right or wrong or whatever?
Yeah.
Yes, Joe's observation correct.
No.
No, Joe's is not correct. And let's show you how we can tell that they did not grow at the same rate. If they grew at the same rate, wouldn't their percent of increase be the same?
Yes.
Does that make sense?
Yes.
Okay, good. So on the next page of the graph, it asks you to figure out the percent, or the next page of the paper, it asks you to figure out the percent of increase. So let's go through and actually do that. Now, I'm going to need Supergirl to give me some numbers here. Let's look at the world population graph, Supergirl. Tell me the population in thousands of millions in the year 1950. What do we get? 2,500. And what about the year 2000? 6,000. Okay, good. Now, if I'm going to do percent of increase, now we don't really do percents this year. You're expected to know that by now. But it helps to do a few problems every now and then just to keep it sharp.
That's 2,000, right?
2,500 and 6,000.
Oh, yeah.
Okay? So when dealing with percents, a very comfortable way to do a percent problem is percent over 100 equals, it's always part over whole, and in this case, the part is the amount of change over the whole would be the original amount. So the problem says what percent, so it's n over 100 equals, now what's the change from 2,500 to 6,000? How much did it change by? A little
3,000.
more specific, 3,500, right? Okay, and then what was the original amount?
2,500.
2,500.
Wait,
Now, it's a little easier to work with if I kill the zeros, okay?
What's that top one?
Change.
No, that A, it kind of looks like above 100.
Oh, that's a percent over 100 equals change over original amount. N over 100 equals, all right, because I'm trying to find a percent, so I put an N there. Now, I kill the zeros, and I'm left with 35 over 25. I cross multiply. I get 25N equals 3,500. I divide by 25, and N works out to be 140. Okay? So if I just crack out the math, just solve the equation. It should be no problem for anyone in this room to solve that equation. So yes, I went quickly, but in all honesty, that's very simple to follow. So we come out with a 140% change when it goes from 2,500 to 6,000. Now let's take a look at the US population graph, and we're going to do the same thing. 1950, 2000. What was the population in 1950? Supergirl. 150. What's the population in 2000? 275. Okay. So, and of course, this is 150 million and 275 million. So, if I want to do the same proportion, percent over 100 equals change over original amount, I want to know the percent, so that's over 100. Now, what is the change? If you go from 150 to 275, what's the change? 125, good. And what's the original amount? 150. Let's do some cross multiplying here. 150n equals 12,500. Divide by 150. And I believe n works out to be 83.3 repeating. But double check that, make sure it works on your end.
Yeah.
Yeah.
Okay? All right. So clearly, they are not growing at the same rate. The red work, the world population, is 140% change over that 50-year period. The blue work, the US population change, is 83.3% growth over that time. How does the percent increase for the world population compare to that for the US population? Clearly, the world increase is greater. Agree? Everybody with me on that? Okay. Scroll up a little, see what it says next. Do the graphs seem to indicate linear or exponential growth? Here's the graphs. Looking at the graphs, do you think it's linear or exponential? Sure looks linear, doesn't it? But the truth is, population growth is exponential. Now, in the last class, they said how could that be? They said, I don't understand how it's exponential.
Because it can never go down to nothing.
Well, what they said is people are dying. So if people are dying, doesn't that keep it balanced and make it go linear? And the person who asked the question was Molly. And it was like the perfect person to ask the question, because Molly sits there, Sarah sits here, their moms are sisters. So I said, do your moms have any siblings? And they said, yes, their mom has a brother. So I said, okay, so we're gonna start with Grandpa and Grandma, and they have 3 children. And they have, I don't know, X, Y, and Z. Now, I said to Molly, how many kids are in your family? And she said 2. And that would be, I'm gonna call it A and B, I know it's Matt and I. Then I said Sarah, and there were 3, so we'll call them C, D, E. And the brother has no children. Now, I asked how old, since Molly and Sarah's moms are twins, I said, how old were your parents when you were born? And it works out that they were 27 years old, okay? So, from Grandma and Grandpa, let's say at age 20, 30 years later, there are not 2, but there are what? 5. Now, let's say a few more years go by. Sarah's now 14, Molly's 14. Let's say they are married by the time they're, and have the children of their own by 30. And let's say child A here, because now there are Molly's side of the family, Molly and her brother, and then there's Sarah and her siblings. Let's say each of these has 2 kids, and this one has 1 kid. Now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 alive, 17 alive, and maybe these 2 died. So a population of 2 has turned into a population of 17 in just 3 generations. And that to me shows an exponential growth, not a linear growth. It's growing very, very fast. Now, how come if this is population, these things look like lines?
Because it's not the whole thing.
That's right. It's not the whole thing. It's a small piece of the graph. And I went on in the last class to explain this, and I drew it all out, and I said, look, at any point in time on a linear graph, if you look, here's a linear, an exponential graph. The piece from here to here, doesn't that look, well, from here to here, doesn't that look like a line? And here to here, and here to here, and here to here, and then here to here. It's when you put them all together that you begin to get the exponential effect out of it. Well, I explained that to them, and then lo and behold, I go a little further down, and there's an excellent picture of it right here. See, if I just, they showed the picture from 1950 to 2000. Doesn't that part look like a straight line? And if I just showed this part, which is all the data I gave, it sure does look linear. But when I back it out and I go all the way back to the year 1700, now does it look linear? No, it looks exponential. So when you deal with an exponential graph, pieces of the exponential graph may seem linear. But when you put it over the entire period of time, definitely not linear. No way, shape, or form. Okay? Any questions? All right. Let's see here. How is it similar? How is it different? Well, this is the piece that's the same. The tail, if you will, here is different because it goes back to a longer period of time. How does behavior in the graph shown in sample 1? Well, we just said the behavior from 1950 to 2000 does look pretty linear in the graph, but when I back it up to 1700, it doesn't look like that in there. How come the graph from example 1 is misleading? Because it only showed a small section of these numbers. You didn't have these numbers here, the 1000, the 0, spread out over the time into the 1700s. So that's how it ended up being misleading. Okay? Any questions? All right, that covers everything we did. We just took knowledge we already had, applied it to a new problem. We'll do a little more of that on Monday, and then we'll go on to a new topic. You may begin your homework.
It's
Did you know that?